Today we are going to learn conditional convergence and absolute convergence. Definition of conditional convergence. Let sigma n is equal to 1 to infinity be the series of real numbers. If sigma an converges but sigma mod an diverges, then we say that sigma an converges conditionally. If sigma mod an converges, then we say that sigma an converges absolutely converges. Second definition. Let sigma n is equal to 1 to infinity be a series of real numbers. We define Pn. We define small p suffix n is equal to an if an is greater than 0 and is equal to 0 if an is less than or equal to 0. We define Pn is equal to an if an is greater than 0 and is equal to 0 if an is less equals to 0. That is, an is negative. Similarly, we define Qn. We define Q suffix n is equal to an if an less equals 0 and is equal to 0 if an is positive, an is greater than 0. An is greater than 0. If an is greater than 0, then maximum of an0 is equal to an, which is equal to Pn. And if an less equals 0, maximum of an0 is equal to 0, which is equal to Pn. Thus, Pn equals, P suffix n is equal to maximum of an and 0. A suffix n and 0. Similarly, Qn is equal to minimum of an and 0. Minimum of an and 0. But we know maximum of AB, is equal to mod of A minus B plus A plus B upon 2. Therefore, maximum of an0 is equal to mod of an minus 0 plus an plus 0 upon 2. Therefore, Therefore, we write Pn equals maximum of An 0, which is equal to mod of An plus An upon 2. Therefore, 2Pn equals mod of An plus An. This is the equation number 1. Also, we know minimum of AB is equal to minus mod of A minus B plus A plus B upon 2. If we take 5 and 2, we obtain 5 plus 2 is 7 and 5 minus 2 is 3. Mod of 5 minus 3 is 3, minus 3 plus 7, it gives 4. 4 by 2 is 2. Minimum of 5 and 2 is 2. Therefore, Qn equals minimum of An 0, which is equal to minus mod of An minus 0 plus An plus 0 upon 2. Qn equals minus mod of An plus An upon 2. Multiplying by 2, we obtain 2Qn. 2Qn is equal to minus mod of An plus An. This is 2. Adding 1 and 2. Adding equations 1 and 2. We obtain 2Pn plus 2Qn is equal to mod An minus mod An cancels. An plus An is equal to 2Pn plus 2Qn is equal to 2An. 2 is not equal to 0. Dividing by 2, we obtain Pn plus Qn. Pn plus Qn is equal to An. Relation between Pn and Qn. Relation between small Pn and Qn, where Pn is equal to An if An is positive and is equal to 0 if An less equal 0, and Qn is equal to An if An is less equal 0 and is equal to 0 if An is positive, that is greater than 0. Now we prove the theorem number 2. Theorem number 2. Second theorem. Theorem second. Statement of theorem second E. If sigma An converges absolutely. If sigma An is equal to 1 to infinity, converges absolutely. Then both sigma Pn and sigma Qn converges. Then both sigma Pn n is equal to 1 to infinity and sigma Qn n is equal to 1 to infinity converges. B. If sigma An n is equal to 1 to infinity converges conditionally. Then both sigma Pn and sigma Qn diverges, then both sigma Pn n is equal to 1 to infinity and sigma Qn n is equal to 1 to infinity diverges. This is the statement of theorem number 2. If sigma an converges absolutely, then both sigma Pn and sigma Qn converges. And B, if sigma an converges conditionally, then both sigma Pn and sigma Qn diverges. Proof of this theorem. Proof. Since by hypothesis sigma an converges absolutely, since by hypothesis sigma an is equal to 1 to infinity converges absolutely. By definition of absolutely convergent series, therefore by definition of absolute convergence, sigma mod an converges. Sigma mod an is equal to 1 to infinity converges. Sigma mod an converges. This is statement number 1. Sigma an converges absolutely. Therefore, by theorem 1, sigma an converges. Since by hypothesis sigma an is equal to 1 to infinity converges absolutely. Therefore, by theorem 1, sigma an converges. That is, every absolutely convergent series implies convergence of series. Sigma an converges. This is statement number 2. Statement number 2. From 1, 2 and theorem 1 on convergence and divergence of series, addition of two series, that is mod of an, sigma mod of an plus an converges. Therefore, from 1, 2 and theorem 1 on convergence and divergence of series. Summation n is equal to 1 to infinity mod of an plus an converges. But we know relation between mod of an plus an is equal to 2pn That is 2pn is equal to mod an plus an. Therefore, summation n is equal to 1 to infinity n is equal to 1 to infinity 2 times Pn converges. 2 times Pn converges. 2 times Pn converges. Therefore, by theorem 1 on convergence and divergence of series, sigma c times 2Pn converges for all c belongs to R, taking c is equal to 1/2. Again we write sigma Pn converges. Therefore, by theorem 1 on theorem 1 on convergence and divergence of series. Convergence and divergence of series. Summation n is equal to 1 to infinity 2c Pn converges for all c belongs to R, taking c is equal to 1/2, we obtain summation Pn converges. Sigma Pn n is equal to 1 to infinity converges. From 1 to and theorem 2 on convergence and divergence of series, sigma from 1 to and theorem second on convergence and divergence of series. Sigma an converges, sigma bn converges, then sigma an minus bn converges. Summation n is equal to 1 to infinity minus mod of an plus an converges. That is sigma an minus mod n is equal to 1 to infinity converges. But we know Qn is equal to 2Qn is equal to minus mod of an plus an. Therefore, summation n is equal to 1 to infinity 2Qn converges. Therefore, by theorem 1 on convergence and divergence of series. If C belongs to R, then summation C 2C into Qn n is equal to 1 to infinity converges. Taking C is equal to 1/2. C is equal to 1/2. Sigma n is equal to 1 to infinity, Qn converges. Hence the proof of theorem second A. Hence the proof of theorem A. Theorem part A. Now we prove the part B. Part B. Proof of part B. Proof of part B. Theorem second B. Since by hypothesis sigma an converges conditionally. Therefore, sigma an converges, but sigma mod an diverges. Since by hypothesis sigma n is equal to 1 to infinity converges conditionally. Therefore, by definition of conditional convergence of series, by definition of conditional convergence of series, conditional convergence of a series, sigma an converges, sigma a suffix n is equal to 1 to infinity, converges and summation mod an, modulus of n is equal to 1 to infinity, diverges. Sigma an converges, but sigma mod an diverges. We prove this theorem by method of contradiction. We claim sigma Pn and sigma Qn both diverges. We claim, that is, we have to prove that both sigma Pn n is equal to 1 to infinity and sigma Qn n is equal to 1 to infinity diverges. Both the series sigma Pn and sigma Qn diverges. We apply method of contradiction. Method of contradiction. Method of contradiction. If possible, we suppose sigma Pn converges. Suppose sigma Pn n is equal to 1 to infinity converges. Therefore, by theorem 1 on convergence and divergence of series, summation 2Pn converges. Therefore, by theorem 1 on convergence and divergence of series. Divergence of series. Summation n is equal to 1 to infinity 2pn converges. 2pn converges. Therefore, this is a statement number 3. Statement number 3. From 1, 3, from 1 and 3, we write sigma 1, 3 and theorem 2. From 1, 3 and theorem 2 on convergence and divergence of series. Convergence and divergence of series. Summation n is equal to 1 to infinity 2pn minus an converges. But we know 2pn equals mod of an plus an. Therefore, summation n is equal to 1 to infinity mod an plus an minus an converges. That is sigma mod an converges. This is contradiction to our hypothesis sigma an converges conditionally. This is contradiction to hypothesis 2, or you may write or sigma an converges conditionally, or sigma n is equal to 1 to infinity converges conditionally. Therefore, sigma pn diverges. Therefore, sigma pn n is equal to 1 to infinity diverges. Similarly, if possible, we suppose that sigma qn converges. Suppose sigma qn n is equal to 1 to infinity converges. Therefore, by theorem 1 on convergence and divergence of series. Sigma 2qn n is equal to 1 to infinity converges. Therefore, summation, this is a statement number 4. From 1, 4 and theorem 2. From 1, 4 and theorem 2. Theorem 2 on convergence and divergence of series. Convergence and divergence of series. Convergence and divergence of series. Summation n is equal to 1 to infinity an minus 2qn converges. But we know 2qn is equal to minus mod of an plus an. Minus mod of an plus an. Therefore, summation n is equal to 1 to infinity an minus mod of an plus an converges. Plus an and minus an cancels, and minus plus mod of an. Summation n is equal to 1 to infinity mod of an converges. This is contradiction to hypothesis. This is contradiction to hypothesis 2, or sigma an converges conditionally, or sigma n is equal to 1 to infinity converges conditionally. Hence, sigma qn n is equal to 1 to infinity diverges. Thus, if sigma an converges conditionally, then both sigma pn and sigma qn diverges. Hence the proof of part B. Thank you for watching the video.